Okay, welcome back. Good morning. And today we are going to continue as part of our course on energy conservation and waste heat recovery. We will continue our discussions on thermoelectric generators. Okay, we already have had 2 lectures on this. So today what we will do is we are going to go into analyzing the performance of a thermoelectric generator. Again, thermoelectric generator, as we know, can directly convert thermal energy that is available to us, and in the context of this course we are talking about waste heat recovery. So let us say we have a source of waste heat, or we have a source of thermal energy from which otherwise would have been wasted, and we can harness part of that energy and convert it to additional electrical energy. All right. So before we move on, I will just want to show or want to mention just one extra thing. See, this is how we saw that a thermoelectric module consists of a series of these NP pairs or PN pairs, thermoelectric pairs, and which are connected in series, and then at the top and bottom we have couple of ceramic plates that kind of sandwich these materials. Now the thermoelectric module can be used for generation of electricity, which is the focus of what we are discussing, and this is how it is done. As we saw, on one we have a series of these N and P types. On one end we have a heated a source of heat Qn coming in, and so that is at a hotter temperature. The other end is at a colder temperature, and what we are seeing is, if we do that, we will be able to give rise to an electric current that will flow through a resistor that is outside. Okay, and that is how we are able to get electrical energy out of it. Now the reverse is also possible. Let us say we have a thermoelectric module and we force a current to flow through that in the manner that is shown over here. Then what happens is it gives rise to a temperature gradient across the junctions, and as a result of which it is possible to remove heat across an adverse temperature gradient, that is to remove heat or transfer heat from a lower temperature to higher temperature, okay, which is what is shown here. And where do we see this otherwise? We see this in a refrigerator. In our refrigerators, what we see is we are able to, in a refrigerator, whatever the way it works is, we are able to constantly remove heat from a lower temperature to a higher temperature. We are removing heat from inside the refrigeration chamber, which is at a lower temperature, and rejecting it to the outside ambient, which is at a higher temperature. Thermoelectrics can perform the same function in this manner. Okay. Only in this case the electrical energy is the input to the thermoelectric module and the temperature difference is output, but in our focus what we are looking at for energy generation, the temperature difference is the input, is the cause, and the electrical energy that we get out of it is the effect. So I thought it is important for us to know the other prominent application of thermoelectrics, which is as a refrigerator or as a cooler, where it is being researched and being also used in several applications. Okay. Okay, now let us move on to the thermoelectric generation, that is used as an engine, which is the left hand cartoon. So let us look into this. If we saw last time, and again we will take just a single pair of N and P type and try to analyze this configuration. Okay. So let us do a little bit of analysis. Analysis for performance. Okay. So what we will do is we will do an energy balance to start with. So let us do an energy balance. But before that, let us look at the different source terms. The first one we will talk about is joule heat. Okay. So let me say what is joule heat. So joule heat is Qj, let us write it as Qj, and that is going to be I squared times R. We know that I squared R heating, and again we will write it as I squared, and what is the R? This is the resistance that is offered by the two semiconductors, one N type, one P type. So R is rho L over A, so we will write it as rho P Lp over Ap for the p junction and rho n Ln over An for the n junction. Clear? So, many a times in future we may denote this whole thing as capital R. Okay. So, I just want to define it right now. Now, it is reasonable to assume, okay. So, let me make that note here, or at least state verbally, it is reasonable to assume that this Joule heat is dissipated equally at the two junctions, at the hot junction and the cold junction. So, reasonable, I would say, to assume that Qj is dissipated equally at the two junctions. Okay. So, if that is the case, again once again let us look at this. We have defined the outer or the external resistance as RL, the current as I, the heat that is supplied is QH, and the heat that is rejected the cold junction as QC. Okay. So, QH QC is defined, we know, and we are looking at, if we operate the thermoelectric module, what are the additional energy terms that we are going to come across. So, the second one we will call it as the conduction heat or Q cond or QC, Q cond, sorry, QC is already Q cold. So, why does this happen? This happens because we know that across any material, if we apply a temperature gradient, there will be conduction of heat, right, because there is no perfect insulator, heat will be conducted however low or however high it is. So, we are going to write conduction heat as Q cond is equal to, what is it, Th minus Tc, okay, times the thermal conductance. What is that? Q is Ka dt dx. Okay. So, therefore, I will write it as Kp, where K is the thermal conductivity, Ap over Lp plus Kn An over Ln. These are thermal conductances, just like these are electrical resistances. So, from our basic knowledge of conduction heat transfer, we know that Q is L over K, thermal Q is delta T times K times the cross sectional area divided by the thickness across which the heat is conducted, in this case the length. Okay. So, again let me just quickly write down that this junction is, this is the length L. So, for N and P it will be accordingly it will be the length of N and the length of P. So, this again sometimes later we may refer to as K. Clear? So, we have Joule heat, we have conduction heat. There is a third one which is very important and which is actually coming from the thermoelectric effect, and that is the Peltier heat. Remember what was the Peltier effect? The Peltier effect stated, or Peltier heat. The Peltier effect stated that over and above Joule heat, there is an additional amount of heat which we call the Peltier heat, which must be removed or absorbed in order to keep the junctions isothermal. Okay. So, we are going to denote that as Qp, Q Peltier, and from Peltier effect what do we know of that? We know that that is going to be equal to pi P2n times the current that flows through it, right. And again this can be shown to be equal to alpha Pn times I times T, and this T can be TH or TC depending on the junction. Okay. So, with these definitions what we will do next is we will actually do the energy balance. So, let us go for the energy balance. The first starting with the hot junction. So, hot junction, we can write the energy balance as QH, clear, plus QH is, again remember, it is the heat input. So, that is what is coming in. What else is the input there? We said that half of the joule heat is dissipated over there. So, Qj, half of Qj, and what is going out? What is going out of the hot junction? Let me bring back the schematic. So, QH is an input, Qj is an input. What is going out of here? The conduction heat will be from the hot junction to the cold junction. So, I will write it as Q conduction, and what else? This is a hot junction. So, therefore, the Peltier heat has to be constantly removed in order to keep it constant, in order to keep the temperature at TH. So, QP. So, let us rearrange this. I will go a little fast now here. So, this will be Q conduction plus Q Peltier minus half of Qj, and we can write it as alpha Pn I Th plus Th minus Tc times K minus half I squared R. Okay. Remember, K and R we have already defined. I am sorry, I kind of swapped these two. So, this is actually Qp and this is actually Q conduction. Sorry, this is actually Q conduction, this is actually Qp. So, this is equal to this is equal to this, but I hope you understand. Yeah. Okay. So, we have got an expression for the QH, which is the heat input, as a function of these different parameters. So, let me box that because we are going to use it later. So, this is going to be an important expression. Second one will be the cold junction. So, similarly, in the cold junction what can we do? What is coming to the cold junction is Q cond. The heat that is conducted away from the hot junction is coming to the cold junction. So, that is an input. Again, the Peltier effect, Peltier heat has to come in because the heat has to be absorbed in order to maintain it at that temperature. Okay. Plus half Qj as before, and what is going out is Qc. All right. So, this again we can write it as Qc will come out as alpha Pn I Tc plus Th minus Tc times K plus half I squared R. Okay. If we do the mathematics, we will get this. Okay. So, this is my other important expression. So, I have got an expression for the heat that is coming to the hot junction and the heat that is being dissipated at the cold junction in terms of various parameters, in terms of temperatures, in terms of the current that is flowing, in terms of the material properties like the conductivity and resistivity, as well as the Seebeck coefficient. Clear? So, therefore, what do I have to do? I have to find out what is the amount of electrical energy or electrical work that I can get out of this thermoelectric module. Okay. And what is that going to be? That is going to be the current times this resistance, sorry, I squared R, that is current squared times RL. So, let us write that down and say, therefore, the electrical energy or work obtained is going to be VL times I. This is the voltage across the load times I, and what is that going to be? QH minus QC, first law of thermodynamics. Therefore, VL, which is the voltage across the load times I, if you now use both the expressions that we derived before, it will beautifully come, lot of things will cancel out, and it will come out to be as alpha times the temperature difference Th minus Tc minus I squared R. Clear? So, therefore, sorry, alpha Pn times I times Th minus Tc. Yeah. So, therefore, what is this? So, therefore, we can also write as VL, which by the way is I times RL, is equal to alpha times the temperature difference minus I, because one of the currents cancel out, and let me write it down as Rp plus Rn, right. So, Rp, as we know, we have defined before, Rp is rho p Lp over Ap, and similarly Rn is rho n Ln over An. Clear? So, therefore, what does this give? This gives I, which is the current that is flowing through it, is going to be alpha Pn, sorry, Th minus Tc, I am sorry, Th minus Tc divided by Rp plus Rn plus the external resistance RL. Yeah. So, what does the current flow depend on? This is an expression that nicely captures all the independent variables on which the current flow will depend on. It will depend on the material properties, because the Seebeck coefficient alpha Pn is a material property. It will depend on the temperature difference. So, higher the temperature difference, higher is the current that we are going to get. It is also going to depend on the dimensions as well as the electrical resistances of the P and N junctions, of the P and N materials, right. So, the electrical resistances, the material part comes from resistivity, the geometric part comes from the length and cross sectional area. And finally, last but not the least, it is also going to depend on what is the external load that I am putting in. Clear? So, the current depends on all these parameters. It depends again, once again, on the material properties in terms of Seebeck coefficient as well as the electrical resistivities of the P and N junctions. It depends on the geometrical properties and the geometric dimensions rather, like the length and cross sectional area of the P and N junctions or the P and N elements, I am sorry. And finally, sorry, it also depends on the temperature difference, of course very very important, and finally the external load. Clear? So, next what we will do is we will continue our analysis and say how do we calculate the efficiency of a TEG. Okay. How do we calculate this? So, let us write that eta, which is normally what is denoted or what is used to denote efficiency. What will be the eta of TEG? The basic definition of efficiency is the work output, which is WL, divided by the energy input, which is QH. Clear? Okay. Here we will also write one more thing, that eta Carnot for a thermoelectric device is going to be 1 minus Tc over Th. We know this, right. So, this is going to be the Carnot efficiency, and the thermoelectric generator efficiency will be definitely much lower than this, but it at this point let us also keep this in mind, and later on we are going to use it. Okay. So, what I am going to do next is this will be a mathematical exercise. Let M is equal to resistance ratio and defined as RL over Rp plus Rn. So, which is the external resistance divided by the intrinsic electrical resistances of the thermoelectric elements. Okay. So, therefore, I can write I, which is the current, is going to be alpha Pn Th minus Tc divided by 1 plus M into Rp plus Rn. Okay. Therefore, the external work WL is going to be I squared RL, and you can show it to be as alpha squared Pn Th minus Tc whole squared divided by 1 plus M squared Rp plus Rn squared times RL is what? M times Rp plus Rn, M times Rp plus Rn. Okay. So, a lot of things will cancel out, and finally, what we will have is M divided by 1 plus M whole squared times alpha squared Th minus Tc whole squared. This does not cancel, unfortunately, divided by Rp plus Rn. Okay. Clear? So, next what we will do is we will move on. Therefore, the efficiency of the thermoelectric generator is going to be WL over QH, which is going to be what we just found, the expression for WL, and divided by QH, for which we had derived an expression before. So, this is my expression for WL, and this was my expression for QH, except that over here I am going to just use some of these M definitions. So, I will put R as Rp plus Rn and so on. Okay. If we do all that, and I will leave it to you as an exercise, you will finally end up getting an expression in this manner: Th minus Tc over Th times, and this will be a long expression, the numerator is going to be simple, it is just an M. The denominator will look something like this: 1 plus M minus half Th minus Tc over Th plus R times K, which is again Rp plus Rn times Kp plus Kn, divided by alpha square Pn times 1 plus M whole squared divided by Th. Okay. This is how it will look. Now, let us spend some time looking at this expression. Th minus Tc over Th, what was this? Okay. If you recall, this is Carnot efficiency. This times I have a factor which encompasses a lot of properties. It encompasses the temperature difference as well as the absolute temperature of the hot junction. It includes the material and geometric properties through the resistances and conductances, and it also includes what is the external load and the resistance of that external load that we have put through this term m. Clear? So, therefore, the efficiency depends on the material properties, the materials that we are using, it depends on the temperature difference as well as the absolute temperature, and it also depends on the external load that we have put in. Okay. So, in order to get the maximum efficiency, we need to try and optimize each of these. Okay. So, one last thing that we will do over here is, this term is very important. I will just circle this term. Okay. So, I am going to define this, let define this by a term z or z. Okay. So, z is actually alpha squared p n, okay, divided by k p plus k n times r p plus r n. Okay. So, this is 1 over z actually. So, this becomes 1 over z. So, this is a very, very important figure of merit. When we talk about thermoelectric, if you go and tells anybody that I am working with thermoelectric, the first thing that they will ask you is what is the ZT value, and the Z typically out of that ZT is this parameter, T of course is the typically either the temperature of the hot junction or the mean temperature of the two. Okay. The Z, as you will see, has dimensions of Kelvin to the power minus 1, that is why ZT is important, okay, to make it non-dimensionless. And what does it depend? It is a function of material properties and geometry, and more importantly material properties, because geometry you can tailor or you can use. So, therefore, what we will end this lecture is by this expression. Therefore, I would say the efficiency of a thermoelectric generator is given by the Carnot efficiency Th minus Tc over Th times m divided by 1 plus m minus half Th minus Tc over Th plus 1 plus m whole squared divided by z Th. Okay. One of the most important expressions in thermoelectric generators is this expression. Okay. So, as we see, the efficiency depends on a variety of parameters that we just saw, and here we have defined something very, very important, which is the figure of merit Z, okay, having dimensions of 1 over Kelvin. So, today we started with doing some analysis, and we are trying to, and what we did was we came up with an expression, but by doing energy balance we came up with an expression for the efficiency of a thermoelectric generator as a function of its material properties, as a function of its dimensions, as well as a function of its circuit properties, in the sense that what is the resistance of the load that I have put externally. Okay. So, in the next class what we will do is we will complete this exercise and we will try to wrap up thermoelectric generators. Okay. So, again hopefully you have learned something new today, and we will continue with this learning in the next class. Thank you very much.